This is the last class that I am going to be gone from. I am actually flying back from Hawaii this evening, so I'll be back around campus tomorrow and Friday if you want to come see me or talk to me about something. Monday is actually Labor Day. It's a holiday, so we don't actually have class on Monday, which means I won't actually get to see you guys for another week unless you want to pop by an office hour or swing by my office. So the next class meeting is Wednesday of next week. Again, Monday is a holiday. Now, the class next week on Wednesday is a really important class. I mean, obviously lecture is important, but the really, really big thing is that lab period is going to be a period where we are going to be preparing for the mineral exam. So really make sure that you're in class next week. On Wednesday, I'll be there, and I want to make sure that you have all of the skills necessary to do really well on the mineral exam. And it's not just the mineral exam that's important. The reason we have the mineral exam is that there's minerals we'll be talking about in class. There's minerals that we'll be identifying when we look at rocks. And if you don't know certain basic minerals, you're going to have a hard time with future classes, with future labs. So really the focus of next class's lab is to make sure you can identify the most important minerals that all geologists should know. So definitely make sure you come to lab next week. Now, what I want to do right now is go over the answers to the quiz that you should have just taken, and then we'll start talking about more lecture things. So starting off with question number 1, which of the following statements is true? In order to be considered to be a mineral, the atoms within the mineral or within the material need to be arranged in an organized fashion. That's one choice. Or, in order to be considered to be a mineral, the atoms within the material do not need to be arranged in an organized fashion. So, should the atoms be arranged in an organized fashion, or does it not matter? It matters. So the answer was A. In order to be considered to be a mineral, the minerals or the atoms within the mineral need to be arranged in an organized fashion. This is the reason why glass is not a mineral. Those atoms or the material cooled so quickly, there wasn't time for the atoms to form that crystalline structure. So instead, they're randomly organized, and that's what makes it not a mineral. Minerals have to have an organized structure. Question number 2, what is contained within the atom's nucleus? So within the atom's nucleus are the protons and the neutrons. The electrons whiz around the nucleus. Question number 3, pretending that you're looking at an atom with 4 protons, 3 neutrons, and 2 electrons, what element are you looking at? And you might have been like, how am I supposed to know? I don't have the periodic table memorized. Basically, are you looking at the second element on the periodic table, the third, the fourth, the fifth, or the sixth? How do you know which element it is? Which number here tells you which element you're looking at? It's the number of protons. So the fact that that atom has 4 protons, that's telling me I'm looking at the 4th element on the periodic table. And you don't have to know what that element is. I actually tell you that beryllium is the 4th element on the periodic table of elements. That must be the element that I was describing. Question number 4, how would you best classify an atom with 4 protons, 3 neutrons, and 2 electrons? So neutrons are neutrally charged. They don't matter in terms of talking about electrical balance. What we're looking at is the number of protons and the number of electrons. We have more protons than electrons, which means it has an overall positive electrical charge. If you have an overall positive electrical charge, that makes you a cation, either because the cation has a T in the middle of it, which looks like a plus sign, or because you like cats. Question 5, what overall electrical charge are minerals seeking to obtain? And they're seeking to be neutrally charged is the answer. So you've got your cations, that's positively charged, your anions that are negatively charged. They link together, they electrically balance each other out. And that's what makes minerals. Minerals are neutrally charged. Those ionic bonds are holding those atoms together in that rigid structure that makes it a mineral. Question 6, which minerals are the most important to geologists? Either those that are of economic value or those that are common in Earth. So which was it? The economic ones like diamonds or those that are really common like quartz? It's the common ones, right? If we want to know what the Earth is like, we want to know about those common minerals that make up the Earth. So it's those common ones that are not probably of economic value that are the ones that are most important to us. Typically, those that are of economic value are rare. And if they're rare on Earth, they're not really helping us understand the Earth, so they are less important to geologists. The most important thing when we talk about minerals is the silica tetrahedron. What is a single silica tetrahedron made out of? If we remember, the chemical formula is SiO4. So that's telling us there are 4 atoms of oxygen for every 1 atom of silicon. So 1 silicon atom and 4 oxygen atoms. That is a silica tetrahedron. Question 8, what is the overall electrical charge of a single silica tetrahedron? So the Si is +4. Each oxygen is -2. You have 4 of those -2s, which means -8. You have the +4 from the silicon, so you have this excess of those negatives from the oxygen. It's overall -4. So silica tetrahedron are not themselves electrically neutral. They are anions. They're looking for cations to link to in order to form neutrally charged things. Those neutrally charged things that form are minerals. So minerals are forming when those cations are linking together with the silica tetrahedron. Speaking of cations, question number 9, which cations are the most important for the formation of most minerals found in Earth's crust? The answer was iron and magnesium. Things like aluminum, they're there, but right, it's a +3 charge. It's just awkward to balance things out. Even things with +2 charges, if the atoms are too big, they won't fit in the crystal structure. Iron and magnesium both have +2 charges. 2 of those will balance out the -4. They are the perfect thing to use in forming minerals in Earth's crust. So that's kind of be the big thing we talk about is iron and magnesium helping to form minerals. And they're actually what makes the minerals green and kind of darkish in color that we see. And then finally, question number 10. This kind of goes back to kind of the introduction of the difference between rocks and minerals. But it says that no matter where you sample it, a mineral should have the same chemical composition throughout. And that is true. Right, so that's one of those main definitions of what has to be true in order to be a mineral. You have to have a single chemical composition throughout. So in today's lecture, I will do a brief review of things we covered last time, and then we will continue to talk about those silica tetrahedron. When silica tetrahedron link together, the type of mineral it creates from that we call a silicate. So you could say the topic is silicates or silicate formation, or how silica tetrahedron link together in a variety of ways. And then once we're done with all this technical silica tetrahedron stuff, we will move on to plate tectonics, which is very chill compared to silica tetrahedron and mineral structure. So get through today's lecture, you've gotten through the hardest part of the class, in my opinion. So again, we've already seen these pictures. I actually drew a little outline on the board, which at some point will be big enough for you to see it. And this is just a review slide. You've seen it before. So again, you should know that oxygen has a -2 charge, and silicon has a +4 charge. You know the chemical formula of a silica tetrahedron. You should know there's 1 silicon for every 4 oxygens. It forms that little pyramid shape. And so if it has 1 silicon and 4 oxygens, again, what's the overall electrical charge of a single silica tetrahedron? Is it neutral? Definitely not. Is it a cation or an anion? We can just do the charges. I mean, maybe you already know the answer, but ideally you just are thinking it through. So again, each oxygen is -2. There's 4 of them, so that makes a -8 overall. The silicon, again, has what charge? +4. So if you have +4 and -8, then overall it is -4. Yeah, and we did the same thing over there. And what I just drew on the board is really, again, the same thing. It's my Jenny version of the silica tetrahedron. Each one of those circles is the oxygen. Each one of those corners of the silica tetrahedron is oxygen. It's -2. Inside there, not drawn, is a silicon atom. It's +4. Or you could do the list way I did it last time. 1 silicon, 4 oxygens. It ends up resulting in SiO4 to the -4. which again makes it a cation or an anion. An anion. It's negatively charged. It wants to be neutral. It is not neutral yet, but it is looking to be neutral. Okay, we already did this. So again, to be happy, it needs some cations. Specifically, we need a +4 amount of cations to balance out the -4 amount. And so we were looking at the pie chart, the major elements there in the crust. And on one hand, there's lots of cations available. Which two cations are most commonly used, though? The iron and the magnesium. Oh, too much going on there. The iron and the magnesium, because they have a good charge, just two of them, and they aren't too big. So again, the calcium, the sodium, potassium, and aluminum, either the ratios get weird because there's 3s and 1s, or they're just too big. They don't fit in the crystal structure as well as iron and magnesium do. Okay, so these are the ones that we're looking at. How many +2 cations of iron or magnesium would you need to balance out one single silica tetrahedron? Again, overall it's -4, so we need +4 to balance it out. So we need 2 atoms. We either have 1 iron and 1 magnesium, or you could have 2 irons, or you could have 2 magnesiums, but because each one is +2, we need 2 of them. So let's make sure we have something like that in our notes. So, I mean, we could even just kind of go here and, all right, those are canceling each other out. So we need cations to balance out these remaining oxygens. And I know, I keep saying this, I know the red's not great, but you can hear me and I've got subtitles. So you need cations to balance out these negative charges. So you need cations to balance out these negative charges. And since we're looking at iron, which is +2, and or magnesium, which is +2, you need 2 of them. So this is going to be case 1. You might be like, how do we have any other cases than case 1? You'll see. So maybe I'll just put it as a heading up here because I have space. I'll say case 1. And I'm going to call this the isolated silica tetrahedron case. So in this first case, the silica tetrahedron are isolated. That will probably make a lot more sense when you see the examples where they're not isolated. So just like run with it right now. They're isolated. Sure, Jenny, whatever you say, isolated. So the silica tetrahedron are basically by themselves. I have my 1 silica tetrahedron, and I have 2 cations attached to that 1 isolated silica tetrahedron, and that's going to create a neutral balance. In fact, we could write the chemical formula out. It can be iron or magnesium, doesn't matter which. You need 2 of them for every SiO4. So this is the chemical formula. You don't have to have all these memorized, but this is the chemical formula of an isolated silica tetrahedron. You have 2 atoms, either 1 iron and 1 magnesium, or 2 irons, or 2 magnesiums. There's 3 different scenarios. But the main thing is you need 2 of these to balance out one of those. This is a neutrally charged mineral. we've balanced out the -4 of that silica tetrahedron, and I've created something that's neutral. In fact, it's a mineral called olivine. Some people call it olivine, so if you were doing this week's lab and you came across olivine or olivine and you weren't sure which pronunciation was correct, either's fine. I always heard it pronounced olivine. I don't think anybody would care if you call it olivine. And so olivine is one of the major minerals you will need to know for the mineral exam. And if you did the labs this week and you did not come across olivine, you messed up somewhere. One of the minerals you were asked to identify ended up being olivine. It's an important one. It's one made out of these isolated silica tetrahedron. Okay, we'll come back. Don't worry. All right, so here is what we are looking at with how this is working. Let me just get rid of my face there. So each one of these yellow triangles is a silica tetrahedron. The dashed versus solid line has to do with the direction the silica tetrahedron is pointing. So if the silica tetrahedron is pointing out at you, it's the solid ones. If the silica tetrahedron, if the point on that pyramid is pointing into the screen, it's dashed. And you don't need to know whether it's pointing in or pointing out. I just wanted you to know that that's what that's talking about. So it's really alternating. It's pointing in, it's pointing out. It's pointing in, it's pointing out. It's pointing in, it's pointing out. Because otherwise there's a space problem. So I don't know if me waving my hands makes it any easier to see what's going on. Let me just grab one of these. So this is my little silica tetrahedron. Here it's pointing at you. This red ball is pointing at you. And if I flip it, and so it's pointing at me, it just alternates. Points at you, points at me. You can't see what I'm doing anyways. Points one way, points the other way, whatever. They're just pointing different directions. And then those green balls are the cations. We either have iron or magnesium, and they are attaching themselves. So it's a little bit difficult to see. Maybe it's easier if you kind of pick a corner here. There are 2 green balls for any one silica tetrahedron. 2 green balls, 1 tetrahedron. 2 green balls, 1 tetrahedron. So there's my 1 tetrahedron. It has an overall -4 charge. I have 2 cations to balance it out. I could then label that one. So I'm just using colors so you can kind of see which one is belonging to which. There's my other silica tetrahedron that's -4. Those are my 2 cations needed to balance it out. Here's another silica tetrahedron with its 2. And we could kind of go around labeling them all. But hopefully if we were to do that, you would see there's 2 cations for every silica tetrahedron. The silica tetrahedron are isolated from each other. They're not touching each other. That's what makes it isolated. What you'll see in some future ones is they will sometimes start to form chains. They'll link up. But right now, the tetrahedron are isolated from each other. Here's another version of it, more isolated silica tetrahedron. Again, each one's a -4, so it needs 2 + 2s to balance it out. That's -4, it needs 2. That's -4, it needs 2. -4, -4, -4. So, yeah, isolated silica tetrahedron. So part of what I think is just really cool about this whole chemistry thing about it, and again, there's my chemical formula, and it's olivine. But what I think is cool is what's written here in yellow, that tetrahedral arrangements are often reflected by the appearance of a mineral. So again, the more we do, the more you'll see what I'm talking about. But if you look at this mineral olivine, it kind of looks like it's made of a bunch of green sand. And there's like one little, maybe like a dark green grain, and there's a light green grain, and maybe an in-between green grain. Whew, that's not easy to say, but they're kind of these isolated little crystals. So you can kind of imagine these are isolated little tetrahedron. In case you're wondering why some are light green and some are dark green, iron tends to make things one shade of green. Magnesium makes it a darker, different shade of green. So depending on whether it's mostly using the iron or mostly using magnesium or some of each, we get these different shades of green. And what will be relevant, actually it was already relevant this week, is that green is considered a dark color. Things with iron and magnesium in them are what gives something a dark color. That they're heavier, denser ingredients. So even like this light green area of the rock, it's still made out of this iron and magnesium. It's still considered to be a dark colored mineral. So if you weren't sure while doing your labs, now hopefully you have an understanding why that green, even light green minerals, we would categorize on the charts as being a dark mineral. Okay, let's see, just another picture, I don't know, it looks kind of like green sand. Yeah, or maybe a bunch of olives, a bunch of green olives kind of piled up together. This is one of the minerals, again, you will need to know for the mineral exam. So learning to recognize its appearance will be helpful. Next week, I'll be doing a review session where I'm going to give you lots of opportunities to learn the names of each one of these minerals for the mineral exam. But if you just kind of want to start it now, olive green, olivine, and it's got olives in it, or it looks like a pile of olives. Okay, I don't know. I've learned things in weird ways. I just make up silly sayings that help my brain remember things. Do what you need to do. So, anyways, to me, it's a pile of olives. Olive green. Okay, but what if there isn't enough iron and magnesium around? So the Earth only has so much iron and so much magnesium. And let's say a bunch of this olivine was formed. Olivine is taking the iron and magnesium, it's attaching to the silica tetrahedron. Any magma that's left behind is now lacking in iron and magnesium. So what will this remaining liquid turn into? Well, I still have the silica tetrahedron. The silica tetrahedron are still -4. It's still not happy. It wants to create something neutrally charged. How else can you do that? And I'm not thinking you actually have an answer. Maybe you do. The way that we actually create neutrally charged minerals when there aren't enough cations around is we start linking silica tetrahedron together. So in that original case, they were isolated. They weren't touching each other. Now they're going to start to link up, forming chains. So that's going to be what I would write in my notes, and I could write it on the board, although honestly, it's there on the screen. I don't know that you really need me to write it twice, so pretend I'm writing that on the board. So option 2, if there are insufficient cations around, it can start linking together and sharing oxygen. So take a minute, write that down. You still might not know what that means. It's okay. Well, I'll explain. So if there are insufficient cations around, the silica tetrahedron, that's the it. The silica tetrahedron can start linking together and sharing oxygen. So let me do some pictures on the screen, and then I'll show you how maybe you could try to write that in your notes. So this is the isolated silica tetrahedron, right? They're not connected to each other. Here, they're sharing an oxygen. I've got little models, but I'll show you once my picture gets bigger. So let's look at how linking together is affecting the overall electric charge of the silica tetrahedron. So in that isolated tetrahedron, we've already been kind of drawing this. It's actually what's still up here on the board. We have SiO4. So 4 oxygens, 1 silicon. Again, each oxygen is a -2. The silicon is a +4. So overall, that has that -4 charge we've been talking about. That other isolated silica tetrahedron, same thing, 1 silicon, 4 oxygens, it's also -4. So if you look at the total sum of those 2 isolated silica tetrahedron, what is their overall electrical charge combined? -8. -4 from the one, -4 from the other. I have -8 that I need to overcome, or I need enough cations to balance out that -8. If there's 2 silica tetrahedrons. I could have had 10 silica tetrahedrons. I'm picking 2 to keep it hopefully relatively simple. I know it might not feel simple, but simpler than the alternatives. So here, the silica tetrahedron are sharing an oxygen atom. So I've got like my one pyramid that's upside down, one pyramid that's sticking up. This oxygen atom right here is being shared between those two silica tetrahedron. So each one has a silicon. This one is O4. It's got the 4 oxygens. Each has -2. This one, in a sense, has 4 oxygens. Each has a -2. Only this oxygen I'm using twice. I'm using it in this one, and I'm using it in that one. So now we just count the charges. We've got a +8. We have a -2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14. If I have +8 and a -14, what's the overall electrical charge? -6. I mean, really, maybe an even simpler way to think about it, each oxygen is -2. There's one less oxygen here because we're sharing an oxygen. So that -2 of that oxygen is gone. So it's now less -2 than it was. So this is what it was. Now there's one fewer -2. So now it's only -6. Good stuff. Okay, so let me just show you in case, I don't know if this is any more helpful. So there's my one silica. Trying to figure out where in the, there we go. So ignore, yeah, just look at the bottom. Perfect, so that's a silica tetrahedron. The red balls are the oxygen, the black ball is the silicon. That is a silica tetrahedron. It's an upside down silica tetrahedron, but again, the black ball is silicon. There are 4 oxygens, those are the red balls. Linked together, it looks like this. That better, there we go. So this oxygen is being shared. So rather than having 4 oxygens here and 4 additional oxygens here, there's one fewer oxygen. There's not a second oxygen here. And because I've gotten rid of an oxygen, I now have gotten rid of a -2 charge. So one fewer cation is now needed. Let me just write the punchline summary here on the board. So case 2 was when there aren't enough cations around. So when there aren't enough cations around, the silica tetrahedron link together, forming chains. So when there aren't enough cations around, the silica tetrahedron stick together, or link together is probably a better word than stick. They link together, forming chains. Each time they link together, they're sharing oxygen. And really an important piece to add here is they're sharing oxygens, or when I'm going to use link. Link's better. When they link together, they link by sharing oxygens. So when they link together, they share oxygens. So I don't know that you need to do it, but let's actually just, yeah, we can do it. So that's by one silica tetrahedron. We can label all of them if you want to. I kind of feel like we just did that. It's over here. -2, -2, -2, -2, silicon in the middle, that's -4. That's another isolated silica tetrahedron, is -4. So again, it needs +8 to balance it out.
which we can accomplish by having how many +2 cations? 4. 4 atoms of iron or 4 atoms of magnesium, or a total of 4 of those things will end up creating the +8 charge, the +8 charge that I need to balance the -8. That was an isolated case. Okay, here's how you draw chains, or how I draw chains. Draw a straight line, maybe a little longer. Perfect. Create a little zigzag. Oof, that was terrible. That's one silica tetrahedron. That's a second silica tetrahedron. That is the oxygen that's being shared. That's the oxygen that's being shared. So there's one less oxygen in this example. So there's one less oxygen. And notice I put -2 next to it. That's actually a really important thing to get. There's one fewer of these in this example. Right? Because we're sharing it. There's not the corner of one and the corner of the other. They're sharing that one oxygen. This means that rather than being -8, it's overall -6. So this means it's -6. Again, this was -8. Which means rather than needing 4 +2 cations, we only need 3 +2 cations. So when there aren't enough cations around, we can link together. And each time we link together and share an oxygen, that's one fewer cation that we need to make the thing balanced. Again, the oxygens are -2. Get rid of an oxygen, that's one less -2 we need to balance with. That's one fewer cation we need. Process this for a moment or two. I mean, once you get it, all of the other cases is just this over and over and over again. It's just really important that you get this case. Okay, so we've just been talking about how through sharing an oxygen by linking two silica tetrahedron together into a chain, that sharing of an oxygen gets rid of an oxygen. The oxygens have a -2 charge. By getting rid of that, now one fewer cation will be needed in order to form that mineral. So if there aren't enough cations around, those silica tetrahedron will link up into a chain. So we just left off with this picture. If I just followed up with some of these questions, let me get rid of my face. So how many +2 cations would each need to become balanced? If this is -8, how many +2 cations do we need? 4. So we need 2 for that one, and then 2 for that one, for a total of 4. In the case of this one, it's -6, so we would need 3 cations. So again, one fewer cation is needed. I know I keep saying this, but yeah, so one fewer +2 cation is needed when an oxygen atom is shared between two silica tetrahedron. So what ends up happening is the silica tetrahedron link together to form chains. Now in the picture I drew on the board, I just shared one oxygen, but in forming a longer chain, we actually end up sharing more oxygen. So if you wanted to try to draw this in your notes, it would look something like this.
Just debating where on the screen to do it. I'm going to pick there. So remember before, you just drew a straight line. And then you can draw the jig-jags as often as you want. So here I'm making the chain 4 silica tetrahedron long. So each one of those is a silica tetrahedron. And so what we're looking at, again, when we're sharing them, that oxygen is being shared. So that means 1 fewer cation is going to be needed. That oxygen is also being shared, so that's a second cation that we don't need. There's another one, and that would also be sharing further along on the chain. That would be sharing further along in the chain. So again, each time we link up, there's just 1 fewer cation that we need. So we call this arrangement conveniently a single chain silicate structure. Or I'll just say a single chain silicate. So some minerals will form these long chains. If you think about those crystal forms, remember there were some minerals that were super elongate. This is the reason why. It's because internally those silica tetrahedron are linked together, forming this long chain. So going back to my picture here, so you have that long chain, a long chain. These are all the silica tetrahedron. And then there's this layer of cations in between them that help link those chains electrically together. Here's another version from another textbook. That's a little bit more like the way I drew them on the board. Again, there's the layer of cations in between. This picture, I believe, is from the Geology Earth Revealed textbook, in case you happen to have that one. But whatever, you can always go online and find pictures. So yeah, yet another version of the picture. So that was the second option. The second option is we form a long chain. Well, it's possible to share even more oxygen, and that's going to be option 3. And I'll write that on the board in a second. You can pause the video and write it right now if you want to, or you can wait for me. I'll write it down too. So you have the single chain, but what if there's even less iron and magnesium around? If there are even fewer cations around, well, again, the solution is we share oxygen. So the more we're sharing, the fewer cations we need. So rather than there being a single chain with a layer of cations in between, we can form a double chain. So option 3, I'm going to write on the board as a double chain silicate structure. So that's my single chain. This will be option 3. And I'll say it's a double chain. So if we drew it over here, well, maybe don't draw this yet. So if you wanted to, this would be the single chain that I kind of had on that previous picture, and then there are a series of cations in between. So these two chains are not touching each other. So again, in the single chain silicate structure, they're not touching. What's going to be different with option 3 is that this oxygen on this corner and that oxygen on that corner, these two oxygens are going to be shared. Those two oxygens are going to be shared. And again, by sharing an oxygen, there's going to be 1 fewer cation in each location that we will need in order to form this electrically neutral mineral. So option 3, so now I'm going to draw the option 3 over here. It's going to start off looking exactly like option 2. Actually, this is going to be a divider. So I don't know if you can see that green line very clearly, but that's one example. This is a different example. Got a little ugly down there at the bottom. There we go. And so now the next one, I'm going to put that line close enough that they're actually touching each other.
not the most aesthetically perfect one. This one I just drew slower and neater. You can draw a neater one in your notes. But again, if it was a single chain, those are the dots that I labeled over here. So single chain, we would just be sharing those oxygens. In this chain, I guess I didn't label them. Again, those would be the ones that are getting shared in the single chain. Again, I'm going to do it over here. So far it looks the same, but again, we have these two additional places that are being shared. So those are two new shared oxygens. So that says two new shared, kind of hard to read my writing there, but two new shared oxygens. So there's two new places where oxygen are being shared. And if I made the chain longer, there could be even more places where they're getting shared. This is where my being messy is kind of biting me in the butt right now. So we could extend the chain further down and share even more. Again, the point is that every time we're sharing an oxygen, that's one fewer cation that's needed. So if there are lots of cations around, we don't have to form chains. You get the isolated silica structure. If there's some cations around, maybe you get a single chain and another single chain. If there's even fewer cations around, we share even more, forming a double chain. Now, these off on this side are not being shared with anything. These on this side not being shared with anything. They're just two chains together, two chains long. So again, we already addressed this, but what effect would sharing these additional O or oxygen atoms have? And again, by sharing the oxygen atoms, by getting rid of the oxygen that was otherwise going to be there, each one of those is one fewer cation that we need. So again, each means one fewer plus 2 cation is needed. That's the punchline for all of these silica tetrahedrons that we're talking about. So those used to be there. There used to be this layer of iron and magnesium in between, but now we can get rid of those three. So in this particular example, 3 fewer cations are now needed to form this double chain. And that 3 number isn't anything sacred. If I had made the chain longer, there would have been more. But again, each time we're sharing, that's 1 fewer cation that's needed. So this is the single chain case, where again, there's this layer of cations in between. So notice all of those +2 charges that had to exist. So rather than being like this, I am going to get rid of a couple of those layers. I'm going to move those chains together so that they link together, and we end up getting this picture. So I've got a double chain and then a little space, and a double chain and a little space, and we would kind of keep going off to the sides with additional double chains. So that is the double chain silicate structure. So here they are next to one another. So you got your single chain, there you have your double chain. And we kind of introduced this a little bit with the single chain. It turns out the crystal form, this is happening so microscopically, it's not a perfect correlation between a single chain and a double chain. They actually get lumped together. You can have either a single chain or a double chain structure. Either way, though, you're really long minerals. So what are the crystal structures, the crystal forms that are really long? If it's super long and skinny, what's that? Acicular, or the needle-like one. The acicular is the word that we use. And if you're long, but just a little bit flat, those are bladed. So minerals with either bladed or acicular crystal forms, internally, those silicas are either in single chains or double chains. And it's not perfectly acicular single chain, bladed double chain. I know logically it would kind of seem like that's the case. It's not that perfect a correlation, so we're just lumping them together. Single chains and double chains result in acicular and bladed crystal forms. So that's why those minerals look the way they do. So what's that crystal form right there? That's acicular. What's that one? That one's hard to tell. Let's skip that one. What's that one? Those are the flatter blades. This one, honestly, is kind of like a halfway in between. There are some kind of long, skinny ones, but they're also kind of flat in areas. So I was just talking in the last office hour with some people that there are often these sort of gray area things. Needles can turn into fibers. Blades and needles can kind of transition one into the other. So this is one where it's kind of like half one, half the other. So if you're ever like, I can't quite tell which is which, yeah, it can be hard to tell because they have very similar internal crystal arrangements, these chains that the silica tetrahedron are forming in. Okay, well, we can just kind of keep on going. So here was my set of double chains. If those oxygens that were sitting there on the ends now get shared, right, if these two are shared, that will get rid of another +2 charge. If these two are shared, that gets rid of another +2 charge. If those two are shared, that gets rid of another +2 charge, because we're getting rid of oxygens in each one of those cases. And the result of this is a silicate structure. Here it goes. They're squishing together. That we call a sheet. And specifically, we call that a sheet silicate. So, I mean, I'm kind of listing this as option 4. If the word option's bothering you, the point is there are these different ways that the silica tetrahedron can arrange. One option of how they can arrange is to keep them isolated. A second option is a single chain. Third option, double chain. Fourth option will be sheet, and there'll be one more option after that. But let's rate this. I'm going to rate it as option 4. Get rid of all that. Is a sheet silicate. And again, we're just sharing more and more oxygen. If you want to try to draw it in your notes, it is a little tedious to draw it in your notes. You would just draw a single chain. And then you add a second one to make a double chain. The triangles should all be the same size. I didn't do that perfectly. A little bit better than the last one I did, maybe. This is where you could pause the video. I just figured you didn't want to sit there watching me draw this over and over again. Ooh, that's not giving me enough space. Okay, so then I have another one. So previously, this corner and that corner were just sticking out, right? This corner, that corner, those corners were not attached to anything. Now, they're all linking together. And we could make another one. So really, this just goes on, I mean, essentially infinitely. I mean, not literally infinitely, but it just goes off and off and off to the side. So we have this big, broad, flat mineral. It looks like a sheet. I don't know that we need to draw them all connecting, but each one of these blue dots that I'm drawing is just another oxygen that's being shared. So there's probably more. I probably didn't label them all, but we have even more oxygen being shared. Again, that just means even less iron, even less magnesium needs to be around. So if that magma is getting really depleted, if we're making all these single chains and double chains and isolated things, and there's really no iron and magnesium left, or hardly any left, then those silica tetrahedron will start to form sheets instead. So that's a picture from the textbook. That's another picture from another textbook or from the internet somewhere. I don't remember anymore. So crystal form. So the isolated tetrahedron are these little kind of sand grains. And then we have the single chain, double chains forming the acicular and bladed crystal forms. What crystal form would you think this would form? It looks like a sheet. Tabular crystal form. And actually, you know what? I don't know that I wrote it on the board. Let's make sure you have it in your notes. So double chain, you should probably have somewhere in your notes that tends to result in either acicular or bladed crystal forms. I don't know if that's going to be, well, it does, it works, it's on the board. That's not cut off. Acicular or bladed crystal forms. So acicular or bladed crystal forms. The sheet silicate results in tabular crystal forms. Sheet silicates result in tabular crystal form. So in lab, you either did or you will run into soon two very flat minerals. One's biotite mica, one's muscovite mica. They're the ones that grow into sheets. They peel into sheets, these really cool, thin-looking minerals. They are the results of these sheet silicates, of the silica tetrahedron all linking together into one flat sheet. So that's what that mineral looks like. One is lighter, one's darker. It's hard to tell in this lighting in this picture whether that's the light colored one or the dark colored one. I think it's probably the dark colored one, the biotite mica, but it's okay if you can't quite tell. But yes, tabular crystal form. This is just showing what it looks like. So you have one of these sheets that are pointing down. You have another sheet that's pointing up. And there's like a little sandwich layer, a little jelly layer of cations in between. And then you have another one where one's pointed down, another's pointed up, and then we have the little jelly of the cations in between. And then this layer here between those two sandwiches, these are very, very weak electrical bonds that break super easily, which is the reason why this mineral peels into those sheets so easily. It's, again, because of the way those atoms are arranged inside. So those are the sheet silicates. Now, if there still aren't enough cations around that we can't even form those jelly layers, they look like jelly to me. It's not literally jelly, but those layers of cations there, if there's not even enough for that, we can share the tip of this silica tetrahedron with the tip of that silica tetrahedron. I don't know how to draw this, so I'm just going to describe it. So the tip of that tetrahedron, tip of that one, tip of that one, they're all sticking out at you. If there's another layer on top where maybe that oxygen is being shared with another tetrahedron that's pointed down at the screen, it's sitting down there on top of it, then every single corner of all the tetrahedron are being shared. So here, so far, we had 3 corners being shared. If we share that one with another sandwich layer, then we're getting 100% all of them shared. That is the final option, option 5, and we call those ones framework silicates. That's kind of my divider there. So option 5. Framework silicates. And again, all 4 corners of the silica tetrahedron are getting shared. All 4 corners of the silica tetrahedron are getting shared. And if all 4 corners of the silica tetrahedron are getting shared, again, that additional corner that we're sharing means yet even fewer cations are needed. So fewer, until really you don't need any cations. You can just attach all the silica tetrahedron together and create a mineral without any iron or any magnesium in it. Things like quartz. So quartz is actually framework silicate. There's no dark stuff in there, no iron, no magnesium. It's just silica and oxygen linked together. The crystal form that these have tend to be very chunky, very blocky. Do you remember what that crystal form is called of quartz that kind of forms these spears? They're not flat spears, but they're kind of elongate. Prismatic. So minerals with prismatic crystal forms tend to be framework silicates. Those with tabular crystal forms tend to be sheet silicates. Those that are acicular or bladed tend to be the chains, single chains and double chains. Actually, I could even put fibrous in there. The single chains that are kind of breaking off is really where those fibers come from. The isolated would be like those grains of sand. Probably the best is equant. Honestly, there are more crystal form terms than ones we got to. So this is sort of a cartoon version, but hopefully you'll kind of get the sense that yeah, it's the chemistry inside that's giving the mineral the physical property that it has. So if we share those, and those iron and magnesiums go away. Sorry, I didn't animate it. And then you have that framework silicate. It's really hard to draw. This is another textbooks version. This is maybe the best one I found out there. But things like quartz. This is potassium feldspar, which is another one that you should have seen in lab this week, or you should see soon in lab. It's one of the ones you need to know for the mineral exam, which again we'll be reviewing next week. This is just a summary picture. Isolated, single chain, double chain, sheet framework from a different textbook in case you like a different perspective. Where did my face go? I hid myself somewhere. Oh well. So yeah, the different ones. Different arrangements, examples of what the minerals look like, just more textbook. I don't know that we need these. I wanted to actually end by showing you these animations. So if you go, I closed it up. Let me pause and show you. Okay, so here's that web page I was just talking about. URLs on the PowerPoint, but I also put it on the homework sheet for you. So if you click on them, it's kind of cool. It's animated, so they'll kind of rotate around. So if you kind of want to be visualizing those isolated tetrahedron from a little different perspective, we have this. You do have to have the flash player turned on in your computer. This would be single chains. Unfortunately, I don't know how to slow it down, so it kind of whips through them kind of quickly, but maybe it kind of gives you a sense of the three-dimensionality of it. Here would be your double chains. It's spinning around. Oh, rotating around. Yeah, but maybe you could take a screenshot and pause it. I don't know. I don't know if these are helpful or not, but your sheet silicate, it just, again, I wish they just did it slower. And then the last one is the framework silicate, where hopefully everything in all directions all connected to one another. So let's see. A right there has what crystal form? Bladed. They're flat blades. What is the silicate structure of something with a bladed crystal form? Either a single chain or double chain would be just fine. Yeah. What's the crystal form of B? And they both have the same. I don't know if you can see that. I put two examples in case it's easier to see one than the other. They both have, what's the crystal form? Not the silicate structure, but the crystal form would be acicular, forming those long needles. And so again, what would what would the silicate structure be? Again, single or double chains. Yeah. Letter C right there is what crystal form? Tabular, looks like little tablets of paper, and the silicate structure is a sheet silicate. And then D, what would you call that crystal form? That one's not perfect, but I don't know, if all the categories I gave you as options, what would you maybe say? I would say equant. They kind of look like little, they're tiny little soccer balls, but they're all the same length in each direction, so I would call that an equant crystal form. It's not the best example, but if you had to pick, it's definitely not, it's not tabular, it's not bladed, it's not acicular, it's not fibrous, it's not prismatic. What's the silicate structure in that mineral? Those are the isolated ones, why you have those little isolated little grains. And then letter E is what crystal form? Prismatic, those long kind of fat spears. And what's the silicate structure of a prismatic crystal form? Those are framework silicates. All right, cool, good deal. Which one would require the most cations? Isolated which contains the fewest cations framework. So again, we started off isolated, requires the most cations. Each time we went to a chain, double chain, sheet, framework, fewer and fewer cations were needed. If there are no questions about minerals, and I'm sure there's tons of things we could talk about, but those are the basics, we're going to move away from minerals in chemistry, and instead we are going to talk about plate tectonics. So let's talk about plate tectonics. In fact, you might want to just put that as a heading in your notes. I'm going to write it. I know it's going to be small on the screen, but I'm just writing plate tectonics. You can do it too. So that just says, and it's cut off from the screen anyway. Actually, it's not. It's just really, really small. That says plate tectonics. Okay, so a little introduction to plate tectonics. The basic premise behind plate tectonics is that Earth's outer shell, which we call plates, and we'll define it more precisely in a little bit, is broken into these pieces called plates. And through time, these plates move around. As they move around, they do things like create earthquakes, they create volcanoes, and whatever happens to be sitting on the plate, like our various continents, they rearrange themselves. So the picture you might have in your mind about what the globe looks like, that's what it looks like at this very moment. If we went back, say, 50 or 100 or 150 million years, the Earth might look very different from what you're used to. These plates moving drag continents along with them. So some continents used to be closer together in the past. Some used to be further apart in the past. The plates move, moving the continents with them. So these are just a few little pictures showing these ideas. So 200 million years ago, the continents were joined together, forming this large, what we call a mega continent called Pangaea. It's actually spelled down here. Just to kind of show you kind of what various continents were. Here's your North America. South America and Africa, we were all joined together. Antarctica was joined down here. India, which is today over here where Asia is, so this is Europe and Asia, Eurasia. It used to be attached to Antarctica and Africa. Australia was also attached to Antarctica. So 200 million years ago, all of the continents were smooshed together, forming one gigantic landmass. And in this picture, they're labeled as individual continents, just so you can see where the various continents were back then, but it really just looked like a giant blob of material. I thought I had a giant blob picture, but apparently I don't. That's okay. So there was a giant blob of land, again called Pangaea, and here's the spelling of Pangaea. There is sort of a silent A. In fact, you might go online, and some people spell it without the A. I think it's a typo without the A, but that's okay. So Pangaea is the name of this huge continent that existed about 200 million years ago. And that's where this class starts. If you take my historical geology class in the spring, we go back to the very first moments that Earth existed. Earth was created, the continents way back then looked very different from today. But through time, as plate tectonics has done its thing, land masses have smashed together, forming the continents as we know them. But 200 million years ago, they looked like what you see here in this picture, forming this mega continent, Pangaea. And I'll write it on the board in a second. So if you want to just get ahead of me and write it on the board, in the last 200 million years, Pangaea has broken apart, and the continents have moved into their current arrangements. So the world used to look like this, and over the course of the last 200 million years, they've moved into the arrangement that is now familiar to us today. And that's what this animation here is showing us. So here we have some chunks of land that are smashing here, forming Asia, and here's a little island going here. North America, South America, and Africa are breaking apart. Australia, India, Antarctica are breaking apart. India breaks free from Antarctica as South America and Africa separate. India swings up north, smashes into Asia as Australia kind of keeps on moving and as the North Atlantic breaks open.
So here it's going to reanimate, and you don't need to know any of these details, but the whole point is I'm trying to show you that continents move. The numbers here are just showing the year. So it started 200 million years ago. Now it's in the 120 million years ago. So continents move around through time. And what's written down here at the bottom, what's causing these continents to move around and rearrange themselves through time is plate tectonics. So plate tectonics is causing the continents to move around through time. We start 200 million years ago with this mega continent, this huge continent called Pangaea. And what we're going to really focus on in this class is what happened between Pangaea and today. How did continents get from that Pangaea arrangement to what we're familiar with right now? Before we do that, I actually wanted to just make a giant version of my face. Okay, so plate tectonics describes the movement of Earth's plates through time. Describes the movement of Earth's plates through time. And if you're like, wait, what's a plate? Well, we'll get there. Just imagine there's like, the Earth is like a hard-boiled egg, and somebody dropped it, and it cracked into these various pieces, these various shell pieces. We call each one of those pieces a little plate. And through time, they're kind of floating around in a mantle underneath them, and as they move around, the continents get rearranged through time. To be fair, the oceans are moving too. Our eyes tend to be drawn to the continents, but actually, let's go back to the video really quick. So if we now ignore the continents and we look at the oceans, so here, like that ocean is shrinking, shrinking, shrinking. Oh, it's filling in. This is, well, it's kind of hard to see there. But here, oh, a brand new ocean is being formed. This ocean did not exist until about 130 million years ago. Oh, here's another brand new ocean that's being formed. Oh, this ocean over here, it's shrinking, it's dying, it's going away. So yeah, it's not just continents that are rearranging. The oceans are moving around too. The whole world is changing through time. So, adding that to what we have up here, describes the movement of Earth's plates through time. And this causes the continents and the oceans to change their shapes through time, or to rearrange through time. So this causes the Earth's oceans and continents to rearrange through time. We start about 200 million years ago. And what I mean by that, again, is just this class starts 200 million years ago. Plate tectonics originated like 4 billion years ago. Plate tectonics has been happening for a really long time. But in this class, we're just going to look at what's been happening on Earth starting about 200 million years ago. So that's what I mean by this. We personally are starting 200 million years ago. Plate tectonics has existed for billions of years. So 200 million years ago, the Earth was smashed together, the continents were smashed together here on Earth, forming one gigantic, huge mega continent or supercontinent, you sometimes hear people say, called Pangaea. So I'm going to say all the continents. It's not perfect, but pretty close. All the important continents, all the major continents. So all the continents were smashed together. Into one mega continent. And mega just means really big. One huge continent, one mega continent called Pangaea.
And again, this letter A right here, people tend to forget. And actually the subtitles might very well be spelling it wrong because often people spell it wrong. So 200 million years ago, all of the continents were smashed together into one mega continent called Pangaea. And this journey of how we got from Pangaea to today is, again, what we're going to be focusing on in this class, and that's what, to a certain extent, the animation is showing us. So that is today, and there soon as Pangaea breaking apart, things are rearranging into the arrangement we are more familiar with today. And we've seen this before. I don't know that we need to keep watching it, although it is pretty cool. So the first thing that we need to talk about is, okay, well, why believe that this mega continent, Pangaea, ever even existed? And even more fundamentally, maybe, why believe the continents are even moving around? So there's really two things I'm going to be attacking in sort of one discussion. One is, why think that the world looked like this? Why think India was attached to Antarctica and Africa? Why think Australia was attached to Antarctica? Why think that South America and Africa were connected? Well, I believe this picture. And then, even if we say, okay, fine, Pangaea existed, why think the continents can move? Once you think Pangaea exists, you've got to go from there till today, so they kind of have to move. But again, we'll be attacking these two things together.
All right, well, there's lots more cool plate tectonic stuff for us to talk about, but we're out of time, so we'll have to cover that next week. Again, reminder, Monday is a holiday, so I will see you all 1 week from today.